Hello, so in this video we'll be talking about the atomic packing factor, and we'll be discussing how to calculate the atomic packing factor for 3 different unit cell configurations. So the first thing we want to take a note of is the equation for calculating the atomic packing factor. So the equation is as shown here. It is the number of atoms times the volume of the atom divided by the unit cell, like the volume of the unit cell. And also another thing to know is that typically the volume of an atom is calculated using the volume of a sphere, which is 4 over 3 times pi r cubed. And then the typical volume of a unit cell is the cube volume, so that will be a cubed. So the first atomic packing factor that we will calculate is for the simple cube. So to start off calculating this, the first thing you have to do is to write down the atomic packing factor equation, which is the number of atoms times the volume of the atom over the volume of the unit cell. So we will first have to calculate how many atoms there are. So if you count all these different sections, you will see that 4 of them make up 1/2. You see that 2 of these are going to make up 1/2. So then combined, you will have 1 whole atom. So we have 1 whole atom for the simple cube. So and for this one, we also know that the volume of the unit cell is going to be a cube since this length is a. So that we will put these into the equation. The number of atoms is 1 atom times the volume of the atom, which you know that the volume of the sphere, as I mentioned before, is equal to 4/3 pi r cubed over the volume of the unit cell, which is a cubed. But we won't be able to solve for the atomic packing factor with this, so we're gonna have to find a way to cancel out one of the r cubes. So for this, we have to see the relationship between r and a, and we see that 2r is equal to a. So then that means if we use these, that 2r cubed is equal to a cubed. So we will plug this into the equation. 1 atom times the volume of the atom, 4/3 pi r cubed, is over 2r cubed. And then you're going to just want to simplify that, so distribute the cubed. You get 8r cubed. Then you can cancel out the r cubes. And then you can go ahead and simplify this. It will be 4 pi over 24, which is equal to pi over 6, which we will get the atomic packing factor for the simple cube is equal to 0.52 or 52%. So this means that 52% of the volume of the crystal is occupied by the atom. So now we can move on to calculating the atomic packing factor for the face center cube. So we first want to identify that this length will be again a, and this is a cube, so all the lengths will be a. So once again, write down the atomic packing factor equation, which is number of atoms times the volume of the atom over the volume of the unit cell. So for this, we're going to have to once again count the number of atoms. So we see, once again, we're going to count these in the corners, and we see that all of them are, like these 4 will make 1/2, and then there's going to be 4 of the same ones in the bottom, so that will make 1 atom. Plus, we have 1 atom, plus we see that there are 1, 2, 3, 4, 5, and 6 halves. So that means that it's 3 atoms. So then we get 1 atom plus 3 atoms will be 4 atoms. So that's what we will use for the equation. So we can go ahead and write it down in the equation. So atomic packing factor equals to 4 atoms times the volume of the atom, which is once again the volume of a sphere, which is 4 over 3 pi r cubed, over the volume of the unit cell, which is going to be a cubed. And once again, we have to try to find a relationship between a and r, which is r is just the radius of the sphere. So we have to find a relationship between them. To find the relationship between a and r, we can see that this will be 1 r, and then this will have 2 r's, and then this will be another r. So this will be 1 r, this will be 2 r, and this will be another r. So if we draw out the triangle, this side will be 4r, this will be a, and this will be a. So if we use this equation, we can calculate the relationship between a and r. So this would be a squared plus a squared is equal to 4r squared, and we simplify that to be 2a squared equal to 16r squared, and we simplify that even more to get a is equal to 2 square root of 2r. And we will use this to plug it into here. So from that relationship we get 4 times 4/3 pi r cubed over 2 square root of 2r cubed. We simplify that, we distribute the cube, and we get 16/3 pi r cubed over 8 times 2 square root of 2 times r cubed. We cancel out the r cubes, and then you can go ahead and just plug the remaining into the calculator, or you can just go ahead and manually simplify it, which would be 16 pi over 3 times 8 times 2, which equals pi over 3 times square root of 2, which is going to equal to pi square root of 2 over 6, which will give you an atomic packing factor of 0.74 or 74%. And that is the atomic packing factor for the base center cube. Now we can move on to calculating the atomic packing factor for the body center cube. So once again, the first step is always to write down the atomic packing factor equation. And the second step will be to count the number of atoms. So we see that once again, we see 1, 2, 3, and 4, that these will make up 1/2. And then we see again that there's going to be another 4 at the bottom, so that will be another half. So then we get 1 atom from those, and then there's a whole atom in the center, which is the body center one, which is another one, which will equal to 2 atoms. So we can use that to put it into the equation, which will be 2 atoms times the volume of the sphere, which is 4/3 pi r cubed over a cubed. And once again, we have to find a way to simplify this in order to calculate the atomic packing factor. So I'm going to draw a cube so that we can better see how we can find a relationship to simplify this. So we'll draw the cube. So for this cube, the relationship is not as easy to be seen, but try to imagine that the same atomic configuration is inside the cube that I just drew. So we will go from one corner to the other corner and draw a line. And try to imagine this in this cube as well. We see that this is 1r, and this will have 2r, and this will be another r. So in total, this will be 4r. And once again, the lengths are all a. And then another relationship is from one corner to this corner, and we'll just call that D. And then if we draw out the triangles separately, so this will be one triangle, here, and then another triangle will be this one here. So for the green triangle, if we draw it out, this would be 4R, this will be A, and this will be D. For the purple triangle, if we draw this one out, this will be A, this will be A, and this will be D. From this one we get that A squared plus A squared is equal to D squared. And from the green one, we get that A squared plus D squared is equal to 4R squared. But we can use D squared and substitute that into this equation, and we get A squared plus A squared plus A squared is equal to 4R squared, and we get this 3A squared is equal to 4R squared. And if we take the square root of it, we get 3A is equal to 4R. And we simplify that, and we get R is equal to square root of 3 over 4A. So for this one, instead of finding what A equals to something, we were solving for R. And now we can substitute R into this equation that we initially had. So then from this, and we substitute it, we get the atomic packing factor is equal to 2 times 4/3 pi, and then we substitute the R, which will be square root of 3 over 4A cubed over A cubed. And then we can simplify this. It will be 2 4/3 pi 3 over square root of 3, 3 times square root of 3 over 64 times A cubed. So then we can cross out these A cubes. And then once again, you can already put this in the calculator. You can just keep simplifying it, which I will, which is 2 times 4 times pi times 3 times square root of 3 over 3 times 64, which will equal to pi square root of 3 times 8, which will equal to 0.68, which means that the atomic packing factor is equal to 68% for the body center cube. And that is how you do the calculations for the atomic packing factor for 3 different unit cell configurations. So the main thing you have to take note of is you have to try to remember the relationship between A and R and use the triangle properties to try to find these relationships in order to simplify and eventually solve for the atomic packing factor. Thank you.